Welcome back. This is the Tutor Wizard. I'm Adrian. Please subscribe right here. Hit the notification bell. We're doing multivariable calculus. Chapter 0 is differential equations. Section 0.4 is second order differential equations. Last time what we did was method of undetermined coefficients. This lecture what we're going to do is more undetermined coefficients. We're going to do the theorem of superposition and show that we can add the solutions. We'll get to that one, and then we'll do some examples about what we were talking about with all these cases of undetermined coefficients and how we use superposition. Let's get to it. Last time what we did, we stated method of undetermined coefficients. Go back and look at that previous video if you can't remember what the statement is. But for now, we're hoping that we have it memorized going into an exam. Therefore, if you're given or where we have to actually eventually find the general solution, we're going to have to first make the guess for this particular solution. Let's just do that in this example. We're going to be given this ODE, and we're given a non-homogeneous function in each case. This is the same one as we did previously, in fact. But this time we have two functions. F of x is x squared e to the x, and our second one is x cubed e to the negative 2x. Let's see what the guess we would make for our particular solution in each case. Solution. For the first one, our non-homogeneous function is f of x equals x squared e to the x. Our general form of undetermined coefficient says if you get on the right-hand side a x to the m, it said k times x to the m times e to the rx. You make a guess of a m x to the m plus dot 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 plus down to a 0 and then e to the r x, and then they had this x to the s, they said, and then they said you make s is 0 if it's not a root of the characteristic equation, you make it a 1 if it's a single root, and you make it a 2 if it's a double root. What do they mean by that? What we're going to do with that now is, to make our guess, we have x squared e to the x. So our r is 1, which is kind of mean, but it's there. Now we have to check if r equals 1 is a root to our auxiliary equation to the homogeneous scenario. Therefore, our auxiliary equation from this is going to be r squared plus 3r plus 2 equals 0. And from that, what we get is what multiplies to give me 2, it adds to give me 3, r plus 1, and r plus 2. I factor this however you want, quadratic formula, etc. That tells me that r1 is negative 1 and r2 is negative 2. They're both distinct roots of multiplicity 1. Therefore, rr is 1, which doesn't equal this one. So this tells us r equals 1 is not a root of our auxiliary equation, r squared plus 3r plus 2 equals 0. Therefore, what do we make our guess? Our guess therefore becomes y particular of x is going to be a, what is our polynomial? Degree 2. So in general, we're going to guess a2 x squared plus a1 x plus a0 times e to the x. And we're not going to have to add in anything like we did in the previous video. We didn't have to either, because r equals 1 is not a root of this characteristic equation. Therefore, this will be our guess for the first one. For the second one, what are we going to have to do? Negative 2 we saw is a root, so we're going to have to multiply by a power of x. Let's see what happens there. 4x cubed e to the negative 2x. Again, we saw our auxiliary equation is r plus 1, r plus 2 equals 0, and that says r1 is negative 1 and r2 is negative 2. Here we have r is negative 2. It is a root of our auxiliary equation this time, of multiplicity 1. It's not a double root, it's a single real root. Therefore, our guess is going to be, we guess for our particular solution, y particular is going to be x to the 1, because it was a single root, this guy, times, and now we have a degree 3 polynomial, a3 x to the 3 plus a2 x squared plus a1 x plus a0 e to the negative 2x. If you didn't notice and check this business, you will have forgot to get this, and nothing will work out when you try to now take the first and second derivative, plug it back in there. But this is what we get, and now what we would have to do is factor that in, and we have a degree 4 polynomial times an exponential function. We then have to take its first derivative, and then its second derivative, and then plug it back into here, and then simplify and find all those coefficients. So this is not going to be as fun as you think, and that's why sometimes you'll agree that we may like variation of parameters, the other method, in the next video. But for now, these are the types of guesses you do. Let's do another one. Example 2, we've got another equation. Find a guess for the particular solution of these non-homogeneous equations in each case. For the first one, what do we have? We have f of x is x squared e to the negative 2x cos pi x. So because we have e, and sometimes it's mean when they have no e in there and you have just x squared cos pi x, that's e to the 0x. So that means it has no real part in there, but I put it in there for you. What that says is R now is, you have to think about this, what the general undetermined coefficient method statement says. In the second case, case B for undetermined coefficients, when you have coses or sines in there, regardless of whether that's there or not, you have to make the guess, this is the alpha and this is the beta they have in the general form. So that says my R is going to be negative 2 plus pi I. That's the alpha, and that's the two complex conjugates, and the other one, R1 and R2, they come in pairs, would be negative 2 minus pi I. It's conjugate. If those are roots of my auxiliary equation, then I have to multiply by the powers of either x to the 1, and then if it isn't, then I don't have to multiply by anything. Hopefully you can see that our auxiliary equation is r squared minus 2r plus 1 equals 0, if and only if r minus 1 squared equals 0. So we have r1, 2 equals 1. We have a double real root. And so this is definitely not a root of my auxiliary equation. Therefore, my guess is going to be y particular of x is going to be, I have a degree 2 polynomial. So I have a2x squared plus a1x plus a0 times e to the negative 2x cos pi x plus b2x squared plus b1x plus b0 e to the negative 2x times sine pi x. That is the guess that you make for the original one. And then now I have to take the derivative again, put it back into here, simplify. Yeah, I like variation of parameters. You'll see. Check the next video. For the second one, we have f of x is 3x, a polynomial, times e to the x. But we just saw r squared minus 2r plus 1 equals 0 if and only if r minus 1 squared equals 0. So r1, 2 is 1. We have a double real root, which is 1. And this is e to the 1x. Therefore, what we're going to have to do is we're going to guess, because it was a double real root, our guess is going to be y particular of x. First of all, everyone forgets, so don't do that. First of all, I have a linear term. That's going to make a guess of a1x plus a0, they say, times e to the x. And then if that r, which is 1, is a single root, you add x to the 1. If it's a double root, which it is this time, you add x squared. That is the guess we should be making. And again, what are we going to do? You're going to simplify that. You're going to take the derivative twice, and then you're going to put it back into here and then solve for a1 and a0. Now, what we're going to do is talk about superposition. What if I want to solve where instead of f being this one or that one, what if it's the sum of the two? What if I use g as this one, and then we do f of x plus g of x? How are we going to solve that? This is what superposition is talking about. Let's do that next. The theorem of superposition principle. Let y1 be a solution of this one, where we have the same left-hand side, just as we were doing before, but we have, say, a first non-homogeneous function, and then we have another particular solution or some solution to the same left-hand side equals some other non-homogeneous function. Then for all c1 and c2, which are real numbers, this guy, which is the linear combination of y1 and y2, is a solution to this differential equation where we have c1 f1 of x plus c2 f2 of x. This is what we mean by superposition. We're to solve this one independently, solve this one independently, and then the solution to this one is just adding those two solutions up, is what it's saying. It's somewhat obvious, but we have to check, and it is true. Let's see what we mean by that. Example 3 is going to tell us what that theorem was actually saying. Superposition says this. If I have this same right-hand side and now I want to find a particular solution to this linear combination on the right-hand side, what I can do is solve y prime prime plus 3y prime plus 2y equals 3x, and then we're going to solve y prime prime plus 3y prime plus 2y equals 10 e to the 3x. We find a particular solution of those, then particular solution to this will just be the linear combination of these two guys. What that says is from the previous video, in fact, go watch that if you want to see how I did that, but from this one, we find out that the particular solution is, first of all, what's the guess? The guess is going to be, I have a polynomial, so my guess is going to be ax plus b, or a1x plus a0. Doing that and putting it in there, I get that we had, it was 3 over 2x minus 9 over 4 was the particular solution. For this one, we made a guess. You can go check what it was. Then we found out that the particular solution was 1/2 e to the 3x. What that tells me is, using superposition, we have that the particular solution to this ODE is going to be 3 over 2x minus 9 over 4 plus 1 half e to the 3x. Now let's give one statement which is going to tell us when we have a unique solution to a second order non-homogeneous ODE. This theorem is the existence and uniqueness theorem for the non-homogeneous case for a second order linear constant coefficient non-homogeneous ordinary differential equation. This guarantees that if we have this initial value problem, there will always be a unique solution in some interval containing our x naught value. Let's go through this. Suppose we have a whole bunch of numbers. These are the constant coefficients a, b, c that are going to be in front of our ODE. X naught is a point that we're going to have specifically for our initial conditions. Y at x naught is going to be some value y0, this is just a real number, and then the derivative at that value x naught in our interval is going to be some other number. We have to have information about the function, and we have to have information about the derivative of the function to solve a second order uniquely. Now what that says is, therefore, if we can find and have some way, we have one right now, undetermined coefficients. So for certain functions, we have a way of finding a particular solution. So find one of those. If yp is a particular solution of this non-homogeneous equation, and we have two linearly independent solutions, y1 and y2, to the associated homogeneous equation. If you check out the previous videos, we do this systematically in a theorem dependent on the roots of the auxiliary equation. That's how you get two linearly independent solutions. Whether you have a single root, a double root, or two complex conjugates, that gives you the linearly independent solutions. We've already done that part. Then it says the general solution to this initial value problem is unique and is given by the linear combination of two linearly independent solutions to the homogeneous solution plus your particular solution. This is the general solution. Now what you have to do is, what this theorem says is, there's always a unique function you can find to solve an initial value problem, or up to these constants. If you don't want to actually solve the initial value problem, it just guarantees the existence every time. It won't be unique, it'll be unique up to those constants they're going to say. The example I'm going to do, I'm probably going to be lazy and not give myself initial conditions because that's an extra step. We'll do that in the next video. But what we're going to do for now is we'll do an example where we have to, what are the two stages essentially? There will be three main stages. The first two stages are going to be look at the homogeneous equation, solve that, use the theorem that tells you whether you have two distinct roots, a double root, or two complex conjugates, you find this two linearly independent solutions. Then you beg, borrow, and steal somehow to find a particular solution to your non-homogeneous equation. Right now we have method of undetermined coefficients. Or in the next video we'll do variation of parameters. Then you have a way of finding a particular solution. Once you have that, the general solution to the ODE will be unique up to those constants, and it's given by this guy. Let's try that once. Okay, to finish off, let's do an example where we find the general solution to a second order linear constant coefficient non-homogeneous equation which involves superposition. What do I need? I need a homogeneous, the two linearly independent homogeneous solutions, and I need a particular solution of this guy. What I would do first is, in the last one we did that one, and then we'll do this one, and then we can get the particular solution. We need that, and then we need the homogeneous solution, and then the general solution is the linear combination of the two. What do we do? First of all, find the homogeneous solution. So step one, set that equal to 0. That's a nice one. We have 1. Y prime prime plus 3y prime plus 2y equals 0. There's the associated homogeneous equation. That immediately gives you an auxiliary equation, r squared plus 3r plus 2 equals 0. If and only if r plus 1, r minus plus 2 equals 0. And that means that we get r1 is -1 and r2 is -2. Two distinct real roots. I go and I look at the video if I can't remember, or I already have it memorized. This is case 1 of the homogeneous uniqueness and existence theorem. That gives me two linearly independent solutions of the form. What do we get? Y1, or what we're going to get is, I'm going to call it homogeneous. Y homogeneous of x is going to be C1 Y1 of x plus C2 Y2 of x, just like it said in the theorem. And what are these now? We know that in case 1, when we get two distinct real roots, this is C1 e to the -x plus C2 e to the -2x. These are our two linearly independent solutions. And what we're going to call the homogeneous part. This happens when you solve non-homogeneous recursion relations and all these types of things. The idea is solve the homogeneous part, find a particular solution, then the general solution is a combination of the homogeneous solution and the particular solution, Diophantine equations, etc. Anyways, now what do I do? 2, I need a particular solution. So it's 2 stages in these non-homogeneous equations scenarios. Find the general solution to the homogeneous part, find a particular solution, and then the general solution is the combination of those. How do I find a particular solution? Using superposition, we found that y particular of x was, for this guy, we found it was 3 over 2x minus 9 over 4. And for this one, we saw it was 1/2 e to the 3x. So that is our particular solution from the previous example using superposition. Therefore, the general solution is given by y of x is equal to c1 e to the negative x plus c2 e to the negative 2x plus 3 over 2x minus 9 over 4 plus 1/2 e to the 3x. This is the linear combination of the two linearly independent solutions to the associated homogeneous equation plus a particular solution to the non-homogeneous superposition equation. Please subscribe right here, hit the notification bell. I'll see you next time.